So I just joined UCLA this summer, and previously I was in Northeastern University. So now let's first look at the introduction. So actually, the reason that we are in this workshop is information networks are very everywhere, right? And if we look at the very popular mining functions for information networks, we can think about clustering. We try to do community detection, right? We do classification. We want to infer the entity profile for the users in social media, for example. We want to do similarity search. For example, we want to find which movie is the most similar for a given movie according to the link information. We want to do recommendation. For example, try to recommend a movie to a user. We want to do link prediction. For example, we want to predict whether a chemical compound is going to be bound with some protein structure, right? So we can do a lot of things by looking at the information networks. But if we look at all those mining functions, we find that actually there's a very important thing that across all the mining functions, which is we try to find the similarity metric between the nodes by exploring the link information that we can observe in the network. Right. So how we can, using the links to preserve the similarity metric information between nodes. There are a bunch of different solutions. And one possible solution, and it's a very frequently explored solution, that we will try to use a link directly to define the similarity. Okay, there are a bunch of very famous working, for example, SimRank, right? We try to define similarity between two nodes if they share some common friends or share some similar friends. And another very interesting work is we try to do random work with restart, right? So we try to, according to the random work, to determine whether the two nodes are similar to each other or not. And we have our work passive, when we facing the heterogeneous information network, and we try to define the node similarity according to meta path, right? So what are the limitations to this link-based similarity matrix? Okay, so if we look at this problem, actually we find that in order to define the similarity between nodes, we actually need to explore the pairwise node similarity. And this is actually so expensive, especially when looking at the real-world network. It's usually very huge, considering WeChat network actually contains 800 million people in that network. So we cannot afford to really store the pairwise similarity, right, for all those nodes. So there's another possible solution, which is that how about we directly map each node into a low-dimensional space. So in this case, we do not have to store the pairwise similarity between nodes, right? Now each node can be naturally represented as a lower dimensional vector. So when necessary, we can just retrieve the lower dimensional vector and compute the similarity, but we do not have to store all the pairwise similarity, right? So then along this direction, actually we can see that there's a very naive solution, because we know that for every graph, for every network, it can be represented as a matrix, right? So if we look at the matrix, for example, we map the left-hand side collaboration network into the right-hand side matrix form, right? So very naturally, you probably think, how about we just treat each row in this agency matrix as vector representation for each node, right? It's a very naive method, but definitely it's not a very nice way. Why? Because again, this network could be so huge. So if you look at the dimensionality for that row, it could be extremely high. So we cannot really afford to use that vector to do the representation. And also, if we just look at a row, single row in this agency matrix, actually we haven't captured the global information, global structure information, right? So if, for example, two nodes, if they do not share the immediate neighbors, actually if you do some cosine similarity, just utilizing their rows, actually their similarity is going to be 0. But definitely it's not the case, because although you do not share immediate neighbors, you probably share some neighbors remotely, right? So that's why we cannot just use this agency matrix and try to represent those nodes. So what should we do? So recently there's a trend. People try to utilize link information in the network and try to embed those nodes into this low-dimensional feature space. But unfortunately, all those methods kind of generate network embedding. That's without any task guidance. I just want to do the embedding. That's all, okay? And the second limitation for those work is that they do not consider that actually in the carrying information networks, it's not homogeneous information network. Actually, there are multiple types of nodes and multiple types of links. How we can utilize those multiple types of link information is pretty challenging, right? So this is a heterogeneous information network we try to illustrate here. So you can consider it's kind of a movie network. And in this network, definitely we have movies, right? And those movies are linked to people who have viewed those movies. And between the people, actually we do have friendship network. And those movies actually link to actors and directors. Okay, it's very heterogeneous, right? How we can utilize the links here, definitely with different semantic meanings, try to represent those nodes into a nice low-dimensional space. All right, so that's another challenge. So in today's talk, basically I wanted to address two challenges. The first thing that with a particular mining function with some task, guide us how we can do the network embedding, or in other words, how we can represent those nodes into nice low-dimensional vectors. And the second thing that since the network is heterogeneous, we do have observed different types of links in this network. How we can model the importance level for different types of links in this task, right? So in order to illustrate this methodology, and in today's talk, I'm going to introduce two applications. The first application is anomaly detection for the categorical events data, okay? And the second application, I want to show that how we can utilize this methodology to do recommendation, okay? So now let's first come to the first application, and this work actually is published in this year's HCI, okay? So the idea is that we want to do the anomaly detection for the so-called heterogeneous categorical events, okay? So for people who have not too much background for anomaly detection, here just illustrate this idea by this 2D data set, right? So the basic idea is that if we look at this 2D data set, and we can find that there are some two main clusters, and there are also some data points or tiny clusters that are very far away from the two main clusters. So usually we treat them as anomaly, right? And in order to detect this anomaly data, actually we can use simple approaches like try to do clustering on these data points, and then for those data points that are far away from the main clusters, probably we can treat them as anomaly. But now when we come to this type of data, which we call categorical events, then we see that it's very difficult to do that, okay? So what is heterogeneous categorical event? So basically you can consider it's, this is example of enterprise network. You can consider that some user at some time, some day, some hour, and they access to some process, and this process actually kind of access some photo, destination process photo, and this destination process kind of visit some other process, okay? And so basically this event can be described by different attributes, and each attribute actually is discrete, and it can be described by those values. Now here we have observed this sort of process-process interaction events, and now if we still want to determine which event is anomaly, okay, then if we still want to use this clustering-based algorithm to do the detection, we face a huge problem. Because in order to do the clustering, of course you need to define the distance between the two events, right? But now, in order to define the distance, you need to define what's the distance between the two attribute values that we have observed in the two events. For example, what's the distance between user 8 and user 4? Okay, it's kind of an impossible task for us to do that. So basically, our solution is that instead of directly trying to define the distance between the two events, we try to define the probability of an event. Because essentially, if we look at anomaly detection, in the previous example, we try to find the data points that are with low density in this whole region, right? So if we can define the probability, and if this probability is low, then definitely it's more likely to be an anomaly, okay? So fortunately, this kind of heterogeneous categorical event data can be nicely represented by an ego network, okay? So now each event here is kind of centered node, okay? And each attribute, discrete attribute, actually can be considered as entities linked to this event, right? For example, for this event, it is linked to some user, and it is linked to some day and some hour, right? And the event also linked to some like source process and destination process and other folders. So basically, this event can be considered as some sort of ego network, right? And now we try to, according to this ego network, try to define the probability for this event. How can we do that? If we just have this ego network, definitely we cannot do that. But fortunately, this user has been participated in other events, right? And this sort of processes and those folders also are linked to other events, right? So according to this interaction, actually it's possible for us to define the probability for the event directly, okay? So formally, then each event here can be defined as kind of a tuple with m types of different entities, okay? So that's how we can like really formalize this event. And what we want to do, again, remember that we try to, using this node representation technique to do the anomaly detection. So now we try to embed every entities that we have observed in this event data into some low dimensional vector, okay? And we want to, according to the current observed data, try to kind of gain those vectors, okay? And once we have gained those vectors, we can use those vectors to define the probability for any event. So the intuition behind this is that if we have observed the two entities interact with each other very frequently, meaning they kind of participate in the same event quite often, then the two entities should be close to each other in their new embedding space, right? And also, if we have observed that the entities linked to this event are close to each other, then the event should be observed with a high probability. Okay, so that's a general idea. So according to this idea, we have defined the probability for each event in this way. So first of all, according to our assumption that when we first kind of assign score to each event, right? So basically for each event, it's ego network. And then we try to explore the pairwise interaction between all the entities linked to that event. For example, the process-process interaction event, right? We try to decompose it into like user interact with day, user interact with like folder, and the source process interact with destination process, things like that, okay? And for each pair of entity, then we try to utilize their vector, like low dimensional vector, and try to measure whether those two entities are close to each other or not, right? So we directly use this dot product to measure their closeness, okay? And then again, as we mentioned that, the type of this interaction is also very important, right? Probably we say that the they interact with the user is not that important, but the destination process and the destination folder, this type of interaction is very important, right? So we need to assign different weight to different types of interactions. And the total score function is going to be a summation over all the pairwise interaction, okay? So now we can assign a score to the event just based on the entity embedding or their entity representation, right? So after we have this score function for each event, the next thing we need to do is like we use a softmax function to turn this score function into a probability. That's quite natural, right? But here, we have a challenge here. Because when we use a softmax function, and if you look at the denominator, okay, we have to go through all the events in this space, okay? But it's usually really huge because if you consider event have like 10 different fields, and each like field or attribute can have like 10 different discrete values, then we have potential 10 to the power of 10 different events, okay? So it's very like computationally expensive to go through all those events and try to get this kind of probability. But never mind, later we have some trick to deal with this situation. So now we have this graphic illustration to our model. So basically, we're going to embed every entity into a low dimensional vector, okay? And then based on this low dimensional vector, we're going to kind of based on each event, we decompose into pairwise interaction. So we can have the pairwise interaction, right? And then we're going to like associate each pair of interaction with some sort of weight, trying to say that which type of interaction is more important or not, right? And then we have got a score function for every event. And then we use softmax function to map that score function to probability. So now we can write down the probability for every event. Okay, so what should we do next? Definitely is trying to do the parameter estimation, right? What are the parameters here? There are two types of parameters. One type of parameters is a low dimensional representation for each entity in this network. And the second type of parameter is the importance score for each type of interaction. Okay, different types of interaction gain different weight. Okay, so as I said, now we're just going to maximize the likelihood to observe the whole event data set. And then we should be able to get those parameters. But there's a difficulty or challenge in the denominator part because of this really huge potential event space. But we just try to like use existing work, very nice existing work, is NCE method to turn this problem, okay, into kind of binary classification problem. So for the details, you can refer to that paper. But now we have a difficult thing here, okay? So because in this NCE approach, we have to define a kind of negative sampling because remember that now we're turning it into a binary classification problem. So we need to know that how we can define a distribution that we can, a negative distribution that we can sample some event that actually is abnormal, okay? So we have done some tricky part. So basically we try to randomly pick an entity type, okay? And for that entity type, we're going to switch the value by doing some uniform sampling. But we keep the remaining part of this event the same, okay? So by this way, we can kind of generate this noise distribution. Okay, so by doing so, basically we have the modeling part, and we kind of have solved this learning difficulty by using the NCE method. Now let's look at the interesting results. Okay, so we have applied our methodology on two data sets, all on the enterprise network. One is a process event, so process interact with process, and second is the process interact with internet. So there are some like kind of entity summarization in this table, okay? And then what we do is that we use week 1 to build our model and try to learn the parameters according to the week 1 information. And then we try to see whether we can detect the anomaly events in the week 2, okay? And we have compared with several state-of-the-art method. And here I want to mention that if you look at our method, APE actually is always perform the best. And I also want to mention that because remember, we also model the importance of different types of interactions in this kind of approach, right? So we also have a special case of our methodology, which is called APE with no weight, which means that we treat every type of interaction equally important, we force the weight as one, as equally important. And it turns out that if we can learn which type of interaction is more important, our performance is even better. Okay, so that's the quantitative evaluation. And we also try to show some case studies of what kind of anomaly we have detected, right? So here is interesting thing, like, okay, for this process SSH, okay, and it tries to access to the port 80, okay. So it turns out that, okay, it's not the case usually, so we can successfully detect it as anomaly, okay. And now there's another really interesting case study, okay. So remember, we wanted to like embed those nodes into kind of low dimensional space, right? So now let's see what do we have done to this type of entity, right? So we haven't used any like heuristic information, okay? And we just try to embed those 24 hours into this map. And it turns out that we can successfully find that actually the hour 0 is close to 1, but also close to 23, okay? So you can see that everything has already told in this data set. And by doing this embedding and this visualization, we can know that which entity is closer to which entity. Actually, in our paper, we also show like which user ID is closer to another user ID. But without this kind of methodology, actually, it's very difficult or almost impossible for us to do that, right? Okay, so as I said, the second type of parameter is that we can tell you which type of interaction is more important, okay? So that's why we also output this like entity type interaction map. So for the process-to-process event data, we find that the most important pairwise interaction is a destination process interact with a destination folder. So it's also very like intuitive, right? So if a destination source kind of try to access to a different folder, which usually is fixed, then probably we need to consider there's something abnormal there. Okay, so this is also a very interesting thing. And like some other things like the source process access like happen in which day, actually it's not that important because probably like every day this source process is happening. Okay, so this type of interaction is not that important. Okay, so that's for the first task. So in this task, in summary, basically like for each event, like we can form it into like heterogeneous ego network, and when we try to like decompose this ego network into pairwise interaction, and we can like map each entity into low dimensional space. And we can tell which type of interaction is more important. And based on these two types of parameters, we can define the probability of event. And then we can, according to whether this event has a low probability, and then we can tell whether it's abnormal or not. Okay, so that's a summary. And then later we have done something else, okay? So if we consider the previous cases, like we try to do something on this ego network, and the second part is like we try to kind of match the two ego networks together to do some sort of recommendation. Okay, so this work is based on our WWW work, and basically we try to learn the importance of the terms for the content-based recommendation system. Okay, so this is kind of background introduction. So actually it's LinkedIn data, right? So in LinkedIn, a very important task is that people try to like recommend the jobs for the user, okay? And actually for their user and for their job, they have so much text data. So that's why they usually try to use this content-based recommendation, okay? And if we look at each like user profile and job profile, we find that actually it's not just a bunch of text. Actually, those texts are actually nicely categorized into different fields, right? So then we try to do the match. We're not computing like a global cosine similarity based on all the text. Instead, we try to first match the fields according to, for example, cosine similarity, and we try to sum over all the different pair interaction of those fields. Okay, so in terms of network view, as I said, actually it can be considered as, okay, this user has a very nice heterogeneous ego network, okay, and this job also has a very nice heterogeneous ego network. Although here, like users and jobs are linked to text, but this text belong to different fields. So the text belonging to different fields can be considered as different types. Okay. So what do we want to do here is actually try to do some sort of link prediction, right? So I have users ego network and jobs ego network. We try to somehow to do link prediction. So let's first look at what's the naive solution here. Okay. Actually, a single solution is like, okay, we admit that different fields actually play a very important role in doing this match, right? So probably we can just for each field for user and each field in the job, and we have a like TF-IDF representation for those words, right? Or for those fields, and then we'll do cosine similarity, and we sum over all the possible fields, right? So then we can get a score for each user and for each job, and then we can do the recommendation. So what are the limitations here, right? So basically the biggest limitation that actually here, if you look at how we determine the feature for each word, we just use TF-IDF, and it's completely determined by heuristic. And how can we tell whether that kind of heuristic is good or not? And whether there is some better way to represent each word, right? So it's not clear. And the second limitation here is that although admitting that we should consider the field match first and then do the summation, but here they did not say that, okay, which field pair match is more important, okay? So in terms of the terminology heterogeneous information network, actually I'm saying that actually we need to consider like different types of interaction should have different importance score again, okay? So now let's first have a brief, like a simple idea to show that why sometimes this TF-IDF stuff does not work that well, okay? So TF actually is like, okay, to show like how often each word is appearing in each kind of document. And the IDF will try to give a global kind of weight, try to reweight that term in terms of that importance, right? So now suppose we again try to use this TF-IDF stuff to do the recommendation. Now let's consider two very concrete words, right? The first is government, and the second is machine learning. It turns out that in LinkedIn data, the government actually has a very high IDF, meaning they appear in field documents, right? So they are more unique than the machine learning, this kind of keyword. And machine learning actually have like low IDF, like machine learning cannot appear everywhere, okay? So now let's see, we have a member which has kind of profile information, right? This guy has done some machine learning work for a government application, right? And suppose now we have two jobs. The job one is completely government agency type of job, and job two is more like a machine learning type of job, right? So if we just based on this IDF, probably the algorithm is going to recommend job one to this person, right? But unfortunately, it's not the case because this guy's skill actually is machine learning. Definitely we should to recommend job two to this user. So that's basically the limitation of like we're doing some weighting just according to our heuristics. So then what should be the solution? Okay, so our idea is that we should use the data to automatically learn a better representation for this word. Okay, so that's the first thing we need to do. And the second, we also need to know that in terms of like doing the field match, we need to know which pair of fields in the job and the user, which pair of fields are more important in deciding this recommendation task, right? So in order to do this, we now propose a two-layer score function. So again, here a score function is for a user job pair. But in our previous task in the anomaly detection, the score function is just for an event. Okay, so that's a difference part. Okay, so in the first layer, actually we try to map each original word feature into a scaled version. So we have a new representation for this word. Okay. And then we try to use the new representation of the word to do a cosine similarity, right? And then we can calculate the similarity between every pair of fields for the user and the job. And in the second layer, we want to know which field pair is more important in determining the recommendation task. Okay, so graphically, the first layer we can represent in this way. So that's the original feature for each word. And then we're going to scale it into another feature, and that's going to be our new feature representation. By using this new feature representation, and we're going to calculate the similarity between the user field S, maybe that's user skill, okay, and also job field T, maybe that's job skill. We want to calculate the similarity between the two fields, okay. In the second layer, again, we're going to do the linear combination of all the field pairs, and then we can calculate a score for this user and job pair. And finally, we're going to use this loss function to determine whether this user I and job J should form a link. Okay. So we, learning-wise, we just use stochastic gradient descent. And now let's come to the experiment part. So we actually use a real LinkedIn data, okay? And then we provide some positive links if this user has indeed taken some job J, okay? And also put some negative cases inside, right? And then by using this data, and we can actually do training and a test. And then we can show a lot of interesting stories here first, because we can now automatically learn which term is more important according to the new representation, right? We just show it here. So it turns out that for the job skills, the top terms, if we look at it, include words like accountant, right? Project, automation, security, things like that. And if we look at the top terms in the member skills, we see that there's something like control, machine learning, and things like that. Okay. And also, we are interested in which field in job should match to which field in user, right? So it turns out that the member skill and the job skill, these two fields, they are the most important thing. It's kind of intuitive, right? Because when you try to recommend jobs, definitely the skills, if the skills of the job and the user match, then it should be the best, okay? So the next important pair is member summary and job description. It's also kind of intuitive. And it turns out that by using our methodology, we can enhance the recommendation success rate by 17% compared to LinkedIn's previous method. Okay, and here I want to emphasize that it's not just for recommendation. Okay, more generally, our methodology can be utilized for any link prediction task, as long as these two entities can be represented as two heterogeneous ego network. Okay, so due to the time, probably I just summarize here. So here, I want to show that actually by representing the nodes into some low-dimensional space, is very effective and efficient for a lot of mining functions. Okay, and also different types of links actually should play different roles if we recall the anomaly detection problem and the recommendation problem. Okay, so although today we have just shown two applications, anomaly detection and recommendation, actually this type of methodology is very general to many other mining functions. So that's it. Thank you.